In order to understand more clearly what's going on with Gauss's method, let's consider the notion of row equivalence. Matrices connected by a row operation are equivalent in this sense if they are used as the coefficient matrices of linear systems with the same constants, then those linear systems have the same solution set. In addition, it turns out that connected by a row operation is an equivalence relation on the set of all matrices. We introduced equivalence relations in an earlier talk at the beginning of the course. Let's look at this notion via two lemmas. Elementary row operations are reversible. Here's the proof. For any matrix A, the effect of swapping rows is reversed by swapping them back. Multiplying a row by a non-zero number k is undone by multiplying it by 1 over k, and adding a multiple of row I to row j, with I not equal to j, is undone by subtracting the same multiple of I from row j. Here we display each operation with its inverse. Row operation connectability is an equivalence relation between matrices. We say that matrix A is connectable to B if a sequence of row operations transforms A into B. The book has the proof. Let's consider an example of this point of view, and then we'll consider a sketch of the proof. Here are two equivalent matrices. The one on the left is not in echelon form. The one on the right is in echelon form. But we could transform the right-hand matrix back to the first with the inverse to row 1 plus row 2. Instead of thinking of the right-hand matrix as the goal, we think of them as two members of a family, that is, two members of an equivalence class. Here's some other 2x3 matrices in the same equivalence class as these two. Okay, so let's sketch this idea that row connectability is an equivalence relation. To be an equivalence relation, row connectability, or row connectable must be reflexive. A matrix must be connectable to itself. It has to be symmetric. That is, if A is connectable to B, then B must be connectable to A. It must be transitive. If A is connectable to B and B is connectable to C, then A must be connectable to C. Here's the argument. Given any matrix, the row operation of multiplying any row by 1 yields the same matrix. This verifies that row connectable is reflexive. Each matrix is connected to itself. The first lemma above, the one about reversible row operations, ensures that row connectable is reflexive. If a sequence of elementary row operations transforms A to B, then starting from B and using the inverse of each operation in the reverse order recovers A. Similarly, if a first sequence of operations transforms A to B and a second sequence transforms B to C, then you can stick those two sequences together and consider the sequence consisting of the first sequence followed by the second sequence, and that's going to transform A to C. So A is connectable to C. The point of this exercise is that an equivalence relation on a set, here the set of all matrices, partitions that set into equivalence classes, and we're interested in organizing and seeing how to understand those equivalence classes. Here's a description of the partition. Let's make the previous role official first with a name. Two matrices that are connectable by elementary row operations are said to be row equivalent. The box below pictures the collection of all matrices, each matrix as a point. Each region is an equivalence class. The region's points represent row connectable or row equivalent matrices. This is a picture of the partitioning of the space of all matrices into classes of row equivalent matrices. One interesting question to ask is, given two matrices, how can you tell if they're the same equivalence class or not? The answer will end up involving reduced row echelon matrices.